Well, in this video we're going to talk about using derivatives to locate the maximum or minimum of a function. And nowadays when you can visualize functions easily using Excel or MATLAB, maybe this doesn't seem too useful, but let's take a look at those relationships. If you don't happen, if you're doing back of the envelope work, you're working with a function. Now, these ideas come in handy. They still come in handy today. So let's take a look at a function which is rises up to a minimum and then drops off from its rises up to a maximum and then drops off from its maximum. We know if we take the derivative that the derivative is just the slope. So the slope is going to be 0 at the maximum. Now, it would also be 0 at a minimum, so the question is, what are we looking at? Are we looking at a maximum or a minimum when the slope is 0 of a, the slope of a function is 0? The variation of the slope is the second derivative, and it's negative across the maximum. That means that we start off positive slope, and the slope just continues to decrease. It decreases towards 0 from a positive value, and then goes in to the negative. So it's decreasing across the maximum, and you can see that here. This is a plot of the first derivative. The function that we're using over here is y is equal to minus 2x squared plus 2x plus 20. An easy one to differentiate. We take the first derivative, we get minus 4x plus 2, and the second derivative, we get a minus 4. So we can see that the slope does what we would expect it to do just from looking at tangent lines and how they vary across the extent of the function, and starts off in the positive, decreases to 0, and then goes into the negative. So the question would be, okay, well, the second derivative is negative, the slopes are decreasing across the maximum. So is that a way to differentiate the maximum from the minimum? When we're at a maximum, is the second derivative negative? Likewise, here we have a function which drops off to a minimum, and as we follow the tangent lines around this function, we see that they start off negative, and then they increase to 0 here at the minimum, and then they continue to increase into the positive. So here we're looking at the first derivative. So we've changed this from a minus sign to a plus sign so that we have a minimum here. Our first derivative is 4x plus 2. Over here, remember it was minus 4x plus 2, and we had a second derivative of minus 4. Now we have a second derivative of plus 4. So the second derivative is positive. And this seems to be a good way to distinguish between the whether a function has is a minimum or a maximum when the slope is 0. We look at the second derivative. If the second derivative is positive, we have a minimum. If the second derivative is negative, we have a maximum. Okay, so let's take a look at another function. We have a little bit more complicated function here. It has both a maximum and a minimum. And then we take a look at its first derivative. And the first derivative over here is a quadratic, and it has two roots, two values of x where y is equal to 0. Those two values of x are plus 1/3, 1 1/3, and negative 2.5. So here we are at negative 2.5, and here we are at plus 1 1/3. So we can see that the slopes are the second derivative is decreasing all the way across. The first derivative is decreasing here, but it's increasing over here across this minimum. So it's decreasing across the maximum, and we have a negative here, and a negative second derivative, and it's increasing across the minimum, and we have a positive here. So positive second derivative, minimum, negative second derivative, maximum. And we can go ahead and plug in those two roots into the second derivative. The relationship for the second derivative is 12x plus 7. When we plug in for minus 2.5, the second derivative is minus 23. So it's negative, and we know it's going to be a maximum. The slope is 0 up here. It's a maximum, not a minimum, because the second derivative is negative. Conversely, the second derivative is positive over here above the second root or above the minimum. So we have a minimum in the function, a place where the slope is 0, but the second derivative is positive, so we know that we have a minimum. So those are the basic relationships of minima and maxima to the first and second derivative. The first derivative is always going to be 0. The second derivative is going to be either positive or negative, telling you that it's a minimum or a maximum. So let's take a look at an example. This is an example that's posed by Waltham in his text on Mathematics, a Simple Tool for Geologists, and you'll find this example on pages 153 and 154. He poses the problem. He says, well, let's figure out what the energy is that's required to produce a fault through this layer. And he suggests that to produce the normal fault displacement, the work is going to be proportional to the length of the fault surface, L, times the fault displacement, M. And if we minimize this quantity, work proportional to L times N, or alpha is just some constant, that we will minimize the work. Now I want you to think about this and use your intuition, because if we minimize the product between L and M, think about what theta would be in order to do that. But let's go through the analysis and just see how it works. So we're going to express the length of the fault cut L and the displacement M in terms of the thickness T and the fault gap E. So we can see over here that cosine of theta is equal to E over M. So the side adjacent over the hypotenuse, this is our dip, theta. We see that the sine of theta is also equal to T over L, the side opposite over the hypotenuse. So we have these two relationships. M is equal to E over the cosine of theta, and L is equal to T over the sine of theta. So, if this is the function that we want to minimize, we're assuming that work should be proportional to the displacement M and the length of the fault cut L. And alpha is just this proportionality constant. Then we need to minimize this function here. And so we have to calculate its first derivative and its second derivative. Its second derivative should be positive or negative. Okay, well let's take a look at so this is our function, and it's these are constants, but we can go ahead and treat it as use the quotient rule. So this be kind of a review of the taking a derivative using the quotient rule. We have f is equal to alpha et. G is equal to cosine theta d sine theta. df, the derivative of these constants, is going to be 0. dg d theta is going to be the derivative of this product, so that we're going to have to use the product rule in order to solve for dg d theta. Okay, dg d theta then, using the product rule, is going to be cosine theta d sine theta d theta plus sine theta d cosine theta d theta. And this is just going to be equal to cosine squared theta minus sine squared theta. So if we substitute all this back into the formula for the quotient rule and solve it, then we find that the derivative dw d theta is equal to alpha et sine squared theta minus cosine squared theta over cosine squared theta sine squared theta. Now, for this to be 0, I mean, we're trying to find out the location of the work, which we want to minimize the work. We figure that's probably the most likely dip of the fault is one that's going to minimize the work, so kind of the path of least resistance idea, then we need to, this quantity up here in the numerator needs to be equal to 0. So that's going to be equal to 0 when the sine squared of theta is equal to the cosine squared of theta, and that happens when theta is equal to 45 degrees. So over here we are looking at, just plug these into Wolfram alpha, and you might show an equivalence between these two results, but this is what the function looks like, and you might ask yourself, okay, where is 45 degrees? This is pi. This is going to be pi over 4. Pi over 4 is 45 degrees, and we can see that it's positive in here, can't we? So we know this is a minimum. And, just using the formula that Waltham works through, he shows that the second derivative is equal to this. And then evaluate that at 45 degrees, we find that the second derivative is positive. These constants are positive. And the result is positive. So that tells us again that we have a minimum. So when the second derivative is positive, and the first derivative is 0, we're at a minimum. And this is just a plot of that function. And again, you can see that at 45 degrees here, we have a minimum in this second derivative. Okay, so this is a good example, and I want you to think about this a little bit. Think about have we really minimized the product of the displacement and the fault cut? And then we'll come back to this next time. And again, think about what we're trying to do, and think about another way to formulate this problem.